Welcome back to Beyond the Patterns. So today I have the great pleasure to introduce Xiaochun Lai. So he has been working with photon-counting CT and in particular with the ASICs technology on the detector side. And he will present today on how to combine the knowledge about the detector, the ASICs, and on the other hand, the physics and deep learning into one system and demonstrate how this can give you much better images for photon counting CT. So it's a great pleasure that we can now start with another episode of Beyond the Patterns. Okay, so welcome everybody. Today I have the great pleasure to introduce Xiaochun Lai. He is from ShanghaiTech, had his bachelor's in China from the University of Science and Technology, then moved to the University of Illinois Champaign and did his PhD focusing on energy-resolved photon counting detectors and SPECT MRI. He is also a Gordon Research Fellow at Harvard Medical School and MGH and followed up there for static CT for space missions and cardiac image reconstruction. Then he went on to be a senior scientist at Canon Medical Research working on photon counting detectors for spectral CT. And in 2021, he joined Shanghai Tech University as tenure-track professor leading the Photonic Sensing and Imaging Group, the PSI Lab, in the School of Biomedical Engineering. He specialized in advanced semiconductor detectors, electronics and imaging systems for biomedical applications, and recent focus, of course, on photon counting CT. Today's talk will be entitled A Physics-ASIC Architecture-Driven Deep Learning Model for Photon Counting CT. And it's a huge pleasure that you're here. Xiaochun, the stage is yours.
Thank you. Thank you for Andrew's introduction. It's a great honor. I'm also very excited to share our recent work regarding using the physics-ASIC architecture-driven deep learning model. Actually, it's a detector model for photon counting CT. So this one is a joint effort between us and also the Southeast University of China. Here is the disclosure. So this project is funded and supported by United Imaging Healthcare in China and also Shanghai Technology Commitment of Shanghai Municipalities to Explore project. Here is the funding ID. And so the overall line of my talk will give a brief introduction of the photon counting CT and include the CT basic fix and also ASIC comparison, application, and challenges. Related work, then introduce our physics-ASIC architecture-guided deep learning model for photon counting CT, and we show some results or preliminary results. And for CT, I think everyone regarding is a basic physics review. So actually, you have a tube, the electron beam hitting your rotating anode. So you get because the electron is speed up, have high energy, then heating is stopping. At the same time, will eliminate a lot of X-ray, generate a lot of X-ray. Those X-rays are multi-spectral. They have a different energy. Then those X-rays are hitting with our object, hitting those patients. Then because the interaction between photoelectric effect and complex scattering, the X-ray would reduce. If you have a high attenuation tissue like bone, then you detect less photons. If you have like the lung or those areas, you will detect more photons. Basic idea, you could using the detector photon do an image reconstruction, get an object of your patient, like where is the electron density of the patient. So conventionally, the detector is using the EID detector. Basic idea, you have an X-ray hitting on the sensor. Those sensors are generating optical photons the number of photons generated is proportional to the energy of your X-ray. But because the X-ray converted photon is very slow, so it's very difficult to separate those photons using scintillator detector. So typically they integrate everything together. We call integrated data acquisition system. Then you get a black white image. If you have a really intense image, like this the hotspot region, and then which means you have a less attenuation. Then here you have a high attenuation. Then you do a reconstruction. Then you get an image. Let's hold the procedures. If we coming back from the early stage of the photon, the detector, the CT development in the 1970s, the first system here is a single slice point phantom. So since the 1970s to 2011, all the effort of CT we call slice world. Basically, you have a single slice, one small tiny slice, like 1 centimeter, then like 1 millimeter, 1 millimeter. Then gradually increase, you want to have more FOV, then you do helical scale. Then you have multiple slices, so your single rotation, then you have larger FOV. In 2020, we get a full coverage of heart, which means you need a single rotation, then you get a heart image. So the early 40 years, even though the image quality is increased, from hardware side, the detector side change is increasing the FOV of your systems. We call it slice world. Since 1911, all the effort are try to get a lower radiation dose, high spatial resolution, and also spectral image. And if you look at the spectral information of our X-ray, actually is similar to the visible photons. Visible photons, you have like the 300 nanometer to the 1600 nanometer. It's multiple colors. Similar, X-ray also is multiple colors. It has a different energy from a few nanometer to sub nanometer. So it's a dynamic. It's similar. It's have a multiple spectrum. If we go to optical image, when we do spectral imaging, it's actually they are using some sensor technology. Basically, in each pixel of your sensor, there's an optical filter, like we call mask. Like this sensor on the top of this pixel, they only allow the green color going through. Then this pixel only allow red color going through. Then like this one only allow blue color going through. So basically, he using a spatial distributor to aspirate whole spectral information. Then you could do a color image. Here is an illustration how color image could benefit. Here is the Einstein in the 19 this Jewish taking a photo. Like if you're using color, you get a much better information recovery. This one is optical world. Similar, if we thought we want to do the spectral image in a CT, the things will be difficult because you could not put a filter in front of your sensor, right? Because which means each X-ray passing through the body have some information of your how body is. Then have some dose penalty. You don't want this valuable photon to be attenuated by a filter before of your sensor. So the detector will be with efficiency of 100%, have to 100% efficiency. Unlike the optical, you could use in filter, then you lose some the detection sensitivity. But for CT, you cannot do that. But your detector doesn't have a capability to separate the spectral information. So how we do that? Conventional, like we change the X-ray source, which means we are using a different color X-ray to shining on the body. Like here's dual source, which one is a Siemens solution. Then like GE using fast KB switching solution, you have a multiple. In one angle, you're using a high energy, and the other angle, you're in low energy, just switching the X-ray. Then Philips are doing another way. They are using a two-layer detector. Which one? Because the first layer are sensitive to the low energy photon. Second layer are sensitive to high energy photon. So you use those different solutions. They could separate, do some like image reconstruction, and you could do the similar thing like the spectral image for optical. Then we could do spectral image for a CT, converting the conventional structure image to a functional image using CT. So, but at the same time, this kind of spectrum separation have a lot of costs. So for this one, you increase in your hardware, from single one detector array, increase in two. Also, this one, you need some change in your sensor side. This one, the energy separation, your color separation is not that great. You need a further improvement. So which means we have a new detector technology recently have developed. Conventional, we're using scintillator. Currently, we're using semiconductor. Semiconductor have some a special property. First one, when single X-ray hitting on, it will generate electric charge. And because it apply a very strong electric field, so the charge pulse generate much faster than the scintillator, the excitation process. This one is in the microsecond. This one could go to 10 nanosecond, which means for the X-ray, you could count each event. If you add a really fast photon counting ASIC, you could measure each photons, deposit the energy information, the current generated. Based on this information, I could separate each X-ray photon, measure each photon's energy to this one, how many photons we have in the high energy, low energy, based on, because different tissue have a different interaction property with different energy photons, then you could do a well separation to get a spectral image. So for photon counting, you can to do spectral image is much easier because you just measure the spectrum of X-ray itself, and you don't need to put a filter or you need to change X-ray. You don't need to do that. That's the first point. At the same time, because photon counting, the pixel is coded using the conventional current generation state of a semiconductor process. The pixel size could reduce, increasing the resolution a lot, typically 1/3 times, even 4 times. The resolution is significantly improved. At the same time, because the noise level, I could count each event above the noise level, which means all I event count. If I count one event, that's a true event. You could eliminate electric noise. So also this one, we also get a spectral information. So this one is the hardware innovation. What can we get from the image side? If we look at this one, we could reduce the radiation dose. A lot of study has done because we could realize 0 electron noise, which I could improve SNR to get a better image, the signal-to-noise ratio. Also improve the CT image quality, which means this one is example. Because photon counting CT have a good detectability or weight for the different energy. Then you could do an inverse estimation for the heavy metal artifacts. He could recover really well. And also, excuse me. So for material decomposition, we say it's similar to the conventional the dual source or KV switching. We could do a functional image. Here is just show how the lamp functioning image. So how the perfusion is going. Here is the hypertonic iodide contrast tumor screening, also a functional image. So from structure to functional, also we could get a much higher resolution. Or let's everyone to pursue high image quality. So basic idea. If you look at the trend of photon counting, or CT, you want to lower dose, higher resolution, also spectral imaging. I just need to change detector, then you get everything we want. So it's amazing. All the vendors like include a different player like Siemens. I see Siemens. It's like do a great job after 15 years effort. They develop a great efforts, great products already. Then you have a GE, then the Canon, Philips, also the United Imaging in Shanghai United Image also put a lot of efforts to get this out as a product to serve the patient care, to get a better patient care and better workflow. So that's a lot of, but at the same time, to get this technology work in a real clinical environment is very difficult. Here is let's few things. Because you converting X-ray from spectrum to measure the multiple beam data, that's a lot of things will distort your energy information. Here include the physics. I will explain the physics first. So here is just show one single X-ray hitting general electron. Simply is detected by single one pixels. But in a lot of cases, this event, the charge cloud generator could separate by 2 pixels, which means the energy information you get in your sensor is not right. It will spread like 100 keV photons. Actually, you get 250 keV or 330 keV and for this distort the information. Second one, it's the pileup effect. Pileup effect is you have 2 photons hit on the sensors. If it happen very close, then your pileup will happen. This one is the ideal comparison, but in the ASIC level, the process will be much more complicated. Typically, one event happened less undershoot. If your second event is on undershoot, your energy information of photon is also distorted. Building above that, the pixel to pixel has a large variation, which means even when you have same X-ray flux, same energy, your pixel response will be very different. This one is a small module we showed. In the whole system, we have a 1 million pixel. Each pixel response very different. Here is 1,000 pixels, illuminated by 100 megacounts of X-rays. And then ideally, you have a uniform response. But because the fabrication, each pixel response very different. Like your output counts could vary 20 to 20%, plus minus 20%. That's very typical. So if you don't compensate to correct or model this response variation, then your image quality will significantly degrade. Here show you have a ring artifacts, they have striking ring artifacts. This one causing your model accuracy. So to get this done, actually a lot of effort has played. One is called calibration. You do a lot of data calibration, then to get the system out. Then you have a model-based. One is polynomial fitting. This one you have few parameters, but I will show this method has some limitation to get it under the real clinical environment. Sensor-based response, which one you're using a pure analytical model, you get it done. But as I showed, the pixel has large variation, and also because the response is so complicated, all your analytical model have some simplification. This simplification sometimes will induce a lot of impact in your system. Third is a deep learning model, which means you get a bunch of training data set, then you do a learning. But the question is, in a clinical environment, you need to constantly calibrate your system. Then you don't want to calibrate the whole system whole week. Then you have 1 day to scan a patient. You want to calibrate in a very short time, which means you have very limited data set. And also you cannot acquire such data set in a long time, right? You need to frequently calibrate. So you want to calibrate accuracy model your system on the very limited data set. This is most challenging part for the photon. You want to do spatial image for photon counting CT. And so actually our group actually is more focused on the hardware, sensor and the sensor and readout electronics. We have a expertise for the sensor, how sensor is working inside this sensor material, and how ASIC is responds you to a charge current. We are expert in the aspects. So we want to use this kind of expertise to facilitate, to improve the model accuracy. So we have a 4-chain model. This model just show if you have different event interaction happened, I could see how I could model how the current will generate in your sensor side, in the sensors electrode side. And after this ASIC, I show how ASIC is response because we know the ASIC architecture. Then I know how the ASIC is response. I also know the imperfect condition of how ASIC, like your baseline, because if you compare event, you have needed some baseline. How baseline will shift over flux. We have some knowledge. So we could incorporate all this knowledge in our 4-chain model. Here's just show 2 event, pileup event. If you have a shorter dead time, your pileups happen heavier. Here, if you have a slow or have shorter pulse event, then you have slow pileup. This 2 event you could separate well. Here it's just show two energy photons. This one don't generate any signal. You remove the threshold down, then you could generate signal. Then you get this one, because pilot you only get one count. You get two counts because your pulse is sharper. So our system could incorporate all the critical physics in this modeling. Then we're thinking, how could we use this one to do our ASIC model? Unlike conventional way, you're just using this data blind train your system. What we do is we train a system. This system is not trying to train all the things. We train this ASIC model to learn some critical parameters, some like ASICs response. For the sensor response, we have charged electric field. Then electric field will affect your response. Then we told the system how electric field change can affect your response, because we have a modeling process. We could model this well. Then we train network, put input different charge electric field. Then those systems learn how electric field change affecting your response. Okay. Similarly, for ASIC side, we know some critical parameter like the dead time, baseline shift, electric noise, how electric noise are affecting your response, because we have our previous developed floor chain model. We use this data, train this network, let the network learn how this critical matter parameter are affecting your system. So basic idea, previous a lot of analytical model. This animal have some simplification. We don't have any simplification, but we let the system to learn those parameter mapping critical parameter of your system, how it affects your output counts. Here is critical part. Just we told if you have, for example, you have critical parameter A, this one you're unknown, but I told the system how A change is affecting your output counts Y. So give the system, you just let him know that, oh, this one is a linear model. This one is just an example. Actually, it's not a linear model, but just told this network learn how this critical parameter affecting your system. It's even though it's a very complicated model, but he know how each critical parameter, like the electric field and the electric noise, how those things are affecting your output counts. I just use a linear model as simplification, as you have a few critical parameters. Oh, this system learn. Oh, this one is a linear model. Now I know later what I do, I just estimate each sensor's this critical parameter of A. So the third part, as we just discussed, the pixel have a large variation. This variation is caused by our critical parameter. So in the last step, we just needed to do to estimate. We just need to estimate this critical parameter just using a few parameters, like here is bow tie filter, here is your charge sharing, here's related to electric field, and also some parameters like the spectral shift, AC energy beams. Those parameters are critical parameters. We're trying to using a few calibrated data set to calibrate. Then after calibration, you do an inverse estimation, then you could do an image reconstruction. That's a very typical process. To validate our model, I will use a prototype system developed by United Image, whole-body prototype system. We work with them with Repoler system in the 2022. Here is the whole system is a state-of-art systems. And here's just show how our calibration is matching our experiment. Here is model estimator. Here is experiment data set. And if you show here, it's just your histogram. What's the error of our model? Basically, you have ground truth minus our model. Then you divide it by your experiment ground truth. Then you could see that the error have a very small bias, and you have a median value close to zero. So which means this model can model your experiment data set really well. And second one of interesting part is this model not only he could match the experiment data variation well, he also estimates some parameter physically is making sense. Our ASIC preset that time is about 16 nanosecond. our estimate is about 16 nanoseconds. Median is very close. And here it's just show your spectral shift because the pulse pipe, because they are flux shifting. You can see the edge pixel have a worse shifting. Also, your electron noise edge pixel have worse shifting. That's what we also know, because the typical edge pixel, because of the fabrication, the performance of edge pixel is worse. So here the it's not quantitatively validated, but its quality told us that our model matched the real scenario really well. Here is our image research. Last step is after you have a model and you have a measured data, then you could do an inverse estimation to get your sinogram, then which means you have a Andrew, it looks like a few chat, is it? Because that's a few questions. Okay. Okay,
yeah,
it's okay.
So there's already questions coming in, and
okay.
I'm gathering them, and so we can discuss them later. So there's a lot of interest in your presentation.
Okay, great. Everyone like it. I really like it. Okay, so the last step after you have your system response, right? Then you do an inverse estimation, and here is a very typical normal procedure. If we don't give detail. Here is you don't do any correction. Then you estimate to basic material PMMA and aluminum. Here is the inverse. Our model showed that here's window is very tight window. Your brain is this one is clinical user clean the window. You can see that we even in this tight window we cannot see any image artifacts. Here is totally distorted. Here is your different image under different energy, because we after do material coding, you could see the different phantom image at different energy level. He's 40, 70, 100, 40, 170. Here is the uniform phantom, gamma X phantom, and also here in the 70 kV have a best performance. Let's be as we expected. And here is the long phantom. Here is really nice. Here is the more quantitative study. We just show the non-uniformity of the different regions, 5 regions. Also different MA. Here is you see the in the worst MA. The value should close to 0. Your ground should close to 0. The most heavy bias is region 2. We have a 3HU, but this one already satisfy clinical needs. Image quality is really decent. It's very consistent. Here also we showed the quantity of your iodine contrast here is similar to image, the functional image we will use to identify quantity decomposition. This one is luminance. You could get an iodine map. Here is ground truth is 2. Here's ground truth is 2, 5, 1, 10, and 50. And then you could see the median value of this one is very close to 5. The mean error is about, in the worst case, is about 2%. In all others, close to 1%. So here is achieving really high accuracy. Also, we check the robustness. First we use the 33 combination, then we reduce to 25, and then reduce 16 combination, because our critical matter is about 16. So we could see gradually if you use 33 combined to 25, your image quality is not induce ring artifacts. Gradually, if you go to 16, they're starting to use ring artifacts like the spot. So it's still have further improve space, but I think it's already very decent after this kind of change. So do a quick summary. So in this, we first photon-counting CT is one of the cutting-edge technology that can affect. He could deliver higher spatial resolution, higher spatial resolution, higher contrast, the lower electric noise and low dose. At the same time, could do spectral image. It could significantly affect the clinical practice and improve the patient care. So it's really every vendor try to develop a new system for new photon counting system. In this paper, we present ASIC physics-ASIC architecture-driven model. And one of our key innovation here, we using the ASIC physics developed model to let the network learn how some critical parameter like the electric field, like that time, how this kind of things affecting your response. After that, we use this network using a few calibrated data sets to train, to calibrate, estimate the parameter for each pixels over 1 million pixels. So after that, you could do image process like conventional material decomposition, as we show, validated by our intensive validate using clinical prototyping system. We show image with good accuracy, includes your quality, no ring artifacts. Also, the iodine map really great, no bias value small, and also we could even 24 calibrated data set, we could calibrate this system really well. So here is just acknowledgement. Here we are photonic sensing imaging lab. Here is my lab. I just finished my midterm review. Here's just this photo is just take a few minutes. I 3 years in moved back to China. I built a great team. This team have so strong. We have a lot of things coming out. So then we have a strong collaborator from the Professor Chun Yang's lab from Southeast University, Jishi from Southeast University, and also we get strong funding support strong support from United Image Group, and also the funding agent from the Shanghai and nationwide. Okay, thank you. Last picture is introduce our campus, because ShanghaiTech is a new established university in China, only 10 years old. And currently we located from Germany. It's a 14-hour driver. Then you go to Pudong Airport. Then you take 20 minutes car taxi. Then you go to this one is our campus. This is a sky highline of the downtown Shanghai. Then here we only have a small campus. Only the undergraduate each year is about 500. Now our faculty is currently about 300 ish. Then basically we have a very small student group, undergrad student, but graduate student were more doubles and triples. The PhD student will be similar to our faculty members. And here is my office. My office actually it's let me find it. Okay, my office actually is here. Okay, it's here. I was sitting here talk with you guys. I'm leaving here. Okay, here is our investor. We have a electron free laser built up. That's 20 billion, I think 20 billion US dollars investment. It was starting build up a whole system here. So it's a small, but it's really great atmosphere for research and development. And our department is bioengineering department. So it's Ding Gangshen, maybe Andrea know him really well. So we have a small, we have a 30 the faculty member in our department. Okay, thank you. Great. That's all my presentation. And if you guys have any questions, just really welcome. We could discuss in details. Thank you, Andrew.
Thank you very much. This was a great presentation. I prepared a little applause. I hope it works. I hope you can hear that.
Yes.
So in Germany, we would knock on the table like this. Very well. So no, really, really nice talk. I do have a couple of questions. There's also a couple of questions in the chat, and I think it would be great to go back to slide 16, because that's the fundamental concept of your algorithm here, right? And
yes,
let me clarify a few things. If I understand it correctly, you're doing this on a per pixel level, or are you
yes
in neighborhoods?
So this process just this model only one model.
Mm-hmm.
This only one model. But for after this model, you just learn how like some parameter, your sensors parameter, affecting your ASIC. Basically, learn the function, whole function of your system. This one only one model, but this model have an input called critical parameters input. So after that, this calibration space, you estimate this critical parameter for all your pixels. But it did take time, but it's using current, you could finish, you finished in 1 hour for the calibration procedures. After the system model is ready, then you could do really quick reconstruction.
Let's stay there. So because, okay, and then the input, do you put in on the left-hand side here, is this a measured spectrum or the ideal spectrum?
That's a good question. So we put ideal spectrum here, but also include some attenuation filter.
Okay.
Like attenuation filter is unknown, which means you have because the ideal spectrum is known. So ideal filter, you plus some filter. This filter is not known.
Yes.
So this one is later. You need to estimate this part. Yeah, this part is at the same time. This function, the network also have some critical parameter as your input.
Okay, so then you have a not entirely known spectrum going in, and then you have like the first loss is about the input spectrum. So there you predict how the settings of your detector will essentially shape the input spectrum, essentially mapped to your binning and all of the parameters that your detector has. And then the second network essentially is estimating how the spectrum will look like after all the different error sources have occurred. Like the loss 2 is what you actually detect. This is like this charge sharing.
This loss 2 actually, because this in this system, your loss 1 and loss 2 data set is no. This one data set you could, because this one is generated by your model.
Yeah, so, and you know that from your simulation, right?
Yeah, I know that from the simulation. So this one is your bin counts output from your simulation. This one is a bin counts the spectrum output from your sensor. So these 2 spectrum is no.
Okay. So the loss 1 is what the sensor measures, and the loss 2 is like what it should report, the corrected
report after the ASIC distortion. Your electronics distortion.
Okay, after the electronics distortion.
Yes.
Okay, and then because in the application case you want the opposite, right? Because when you use that for correcting the ASIC artifacts, you want to invert it, right?
Yeah. After in the real case, let's 2 step, because this one is the learning step, right?
Yeah.
Learning model step. So this one you want to let the network learn how those parameters change. It's affecting. This one is your cost function, right? That's first step. When you do, that's another step. Second step, because this network have some critical parameter. So in your experiment, you have another cost function. Just your measure the experiment data compared with your network parameter after change the critical parameter. I think here.
And this is how you, because later on slide 21 you invert because if you go to slide 21, they report like ASIC parameters.
Yes.
The spectrum shift, the dead time, spectrum noise. But this is then the result of you run an inverse problem on your network, right? Because if you know the ideal input and the ideal output, then you can use like a minimization over your ASIC parameters on the network, and then find the maximum by essentially rewiring it, right?
Yes. That basically, ideally, I didn't explain. Maybe I didn't explain quite clear. So let's three inverse estimation. First step is ask a system to learn how your parameter change will affecting your, this one is one inverse, this one using pure simulation data set based on our comprehensive model. The second is our calibration process. This one is to learn using experimental data set to learn how to estimate, because this model has some clinical parameter. They need to estimate pixel by pixel. The second, then you have a third inverse. After you do a patient scan, then you need to inverse the sinogram of your material. So three inverse process. I didn't give too much detail. Here is your second inverse. Just estimate the critical parameter here.
I see. Okay. Okay. And then you have. But do you do that as optimization problem, or do you train a network for the inversion?
Optimization. Yes.
Yeah, that's what I thought. Well, that's really useful, because it may be hard to determine these parameters only from the trainer, because only from the data you would have to run many simulations and then pick the simulation that matches best in order to determine this. And this way you can directly get it from the data with the network, right?
Yeah, yes. Which means, I think I would really proud this model, because which means your model is well predictable, right? It's explainable. Also, it's well constrained. Because we do conventional deep learning, we could see that like fit really well in your training data set. But if you pay off, because your data set is so limited, you could see that the response is loss outlier point. If you don't have a training data set, you could see that they have a lot of bias. So this one you could it could compensate. Like you have limited data set, then I model using some already know physics. I constrain it well. At the same time, this model can be explained really well. This one is, you could see that, as I say, our preset that time is 16. Then he predict median value close to 16. So I think, even though I don't know the real that time it is, but you say, it makes sense somehow, giving me some confidence works.
This is very cool, because there's also a question that does actually also mean you can generalize to hardware that you haven't seen, because you train just with ASIC parameters. That if your training set of ASIC parameters, you can sample across hardwares that you don't even have access to yet, but then you get an unknown detector, you can still use it to figure out the parameters of that new hardware, right?
I think that's one thing. I think there are few constraints here. If you give me new hardware, like sensor, I could. If you give me a new sensor, I just need to run this simulation, okay? Because the pixel size is different. Then if you give me your ASIC is different, I need to know how your ASIC model it is, the architecture-wise model it is. Then I could retrain this model. Then I could do it. I don't need to, you see what I mean? So this ASIC architecture is specialized, used in our current detector. So if you give me new hardware, I just need to ask the vendor, tell me what's your ASIC architecture it is. Then I could redo this thing very quickly.
Yeah, but
so it's very fast. You don't also very generalized.
But from a conceptual point of view, it should work for all ASIC hardwares, right? As long as as you have the appropriate hardware setup in your training data, right?
Yes.
It's fascinating. I have one question on slide 26. You say that you're using different number of combinations, and I wasn't sure what combinations you're referring to. So the 26.
Yes.
Here you have 33 combinations, 16, and I didn't understand what the number of combinations is. Is that how often are you using ensemble of networks? Do you have multiple prediction candidates?
Yes, this one just you could read it as a training data set. You have a 33 training data set for each pixel, 24 training experiment points, 16 points. You have a different spatial information. Like it's just a data point for training each pixel.
Okay, but then it's only training data or also number of trained networks?
Training data for each pixel. But you still use experimental data for each pixel.
Okay.
But you can take all your pixels data 16 times, then you get this 16 experiment.
Because that would be a competing technique to get robustness, that you train multiple network candidates and then average over the predictions of the network.
No. This one, you have a same network structure for all the pixels, but because this step, when you calibrate each pixels, because you need the experiment data, right?
Yes.
Then you just 16 experiment data to estimate these critical parameters.
Okay, then this refers to the amount of work you need in the calibration process.
Yes.
I see. Okay, cool. This is exciting work, and this is also exciting technology, photon-counting CT, because it enables so many new applications in a clinical point of view, right? Material decomposition, then you get tissue properties, not just absorption. So that's super cool, and really, really exciting work.
Yes. Siemens working on photon counting for 15 years. They deliver products now. So all the vendors are trying to do that, like GE, Canon, Shanghai United Imaging. So all the major players are doing it. So excited. I'm really glad that I could be part of this process. So try to see how it goes. I hope less some I think in previous he was the Europe RSA, similar to United RSA, the chair. He said that in the future every city will be photon-counting CT. Let's see where it will become true. So it's still a lot of effort to go.
We don't have black and white television anymore as well.
I agree.
Everybody wants to have color television.
Yes, maybe in a museum. Yes.
Xiaochun, this was a wonderful presentation, exciting research, exciting technology. Thank you for coming here and delivering this talk. And I wish you really, really much success in your research, and I hope you keep up this really cool line of research. And thank you for giving the presentation.
Thank you for your invitation and giving me the opportunity to share my study, because this one is a great community. Everyone try to share exciting things, right? Oh, this one is what I do. I think I'm so smart. I could figure it this way. So it's a really great opportunity for me to share. Thank you.
Absolutely. And I have another round of applause for you, and I hope you can actually hear it. But I'm not sure if my Zoom is set up correctly that it will actually broadcast the noise. Maybe it just cut it out by the noise filter. I don't know. Okay, so then I'll stop recording